Hi, I'm Michael Ossmann of Great Scott Gadgets. Thank you for joining me here at the TAPR forum at Hamvention, and thank you to TAPR for having me here to talk about our project to build a universal radio test instrument. We call our project URTI, which stands, of course, for Universal Radio Test Instrument, and this is just a working title. We do expect to choose a more interesting name when the project is completed. But this is the title that we use for now, and we're publishing information as we develop the project under this name. It's an open source hardware project, like all of our projects at Great Scott Gadgets, with open source software. If you're like me and you've been experimenting with radio technology for some time, you probably have a collection of test equipment, like I do, things that you've pieced together from purchases made maybe at the Hamvention flea market or on eBay. And you have this collection of test equipment that is bulky and heavy, very capable, but quite expensive. Even at flea market prices, you're looking at thousands of dollars of test equipment just in this one photo. And if I had purchased these things new instead of used, this would be tens of thousands of dollars of test equipment. It really, I think, makes the hobby of radio experimentation inaccessible. So we're trying to change that, and the way we hope to change that, the way we hope to make radio experimentation more accessible, is by creating a tool that is a test instrument, a single test instrument that can do the job of several pieces of RF test equipment. And we think that such a device can be made low cost and open source and portable. These things all are important for accessibility, in our opinions. And part of the reason we think we can do this is because RF test equipment these days typically is actually software-defined radio under the hood. And we know a thing or two about building software-defined radio platforms, which is a technology that is much easier to build today than it has been ever before. And we think that we can use this SDR technology to build a tool that meets these requirements. We planned several functions for the device. We wanted to operate as a spectrum analyzer and as a VNA, or vector network analyzer. We wanted to also work as a vector signal generator and vector signal analyzer, also as an antenna analyzer and power meter and frequency counter. And lastly, we wanted to operate as a full duplex SDR transceiver, either in handheld mode or as a USB peripheral connected to a host computer. Many of these functions are things that you may have done with software-defined radio platforms in the past, but the solutions that you've come up with probably, in many cases, are not as great as they would be if you had a dedicated tool or a tool that was really designed for these functions. In particular, the vector network analyzer function is something that is difficult to accomplish with off-the-shelf SDR equipment. It requires, at a minimum, the addition of some external hardware in the form of a directional coupler, and in most cases, quite a bit of software work. This is an open source hardware project, and like many open source hardware projects, we expect to build upon previous open source projects that have come before. And one of those, of course, is HackRF One. If you are familiar with me and my work at Great Scott Gadgets at all, you're probably familiar with HackRF One. It is our software-defined radio platform. It is a half-duplex transceiver with quite a wide operating frequency range. And because it's half-duplex, it can't achieve many of the functions that were on the previous slide. But it is fundamentally a vector signal generator and vector signal analyzer, and it is used as test equipment in that way. And I've always thought of general purpose SDR platforms as being test instruments, but we think we can take that concept much further and make a much more useful test instrument, building upon the successes of things like HackRF. Another project that we're building upon is PortaPack H1. After Jared Boone helped me design HackRF One, he went on to create PortaPack H1, which is an add-on board that turns a HackRF into a handheld, standalone, software-defined radio platform that does have some test instrument functions. And this is a very powerful tool, and it's quite a popular add-on for HackRF One. We don't expect to be really building upon this design directly, but we do see this as an inspiration for our project. We really want to take this concept of a handheld SDR platform further and make it more useful as test equipment, more useful as a portable platform. Another project that really inspires us, that's an open source hardware project that many of you, I'm sure, have seen, is NanoVNA. And there are a number of low-cost portable vector network analyzers available today. Most of them are derived from this original NanoVNA. And when this was originally released, I was so excited about it, and I'm sure many of you were as well. The thing that really struck me about this project was it's tremendously low cost. I think the original one still sells for around $50. And the fact that you can build a useful VNA at such a low cost in a portable platform and make it open source hardware is incredible to me, and really inspires us. It's not the greatest VNA in the world. It has plenty of limitations, but it is useful, and I'm sure that many of you have found it to be so. A project that we are definitely building upon at this point is Cynthion, which is our USB test instrument. And Cynthion is based on the Luna framework, which is Luna is a gateware framework for creating USB gateware on FPGAs. The field programmable gate array is the major component in the center of Cynthion. And basically the architecture of Cynthion is that it is one FPGA in the middle surrounded by USB physical layer transceivers for various USB ports. This is a really useful architecture for creating a USB test instrument, but it's also a useful architecture for creating any USB device that you want to have an FPGA on in particular. So we see Cynthion, at least the portion of it that is the FPGA and one USB port, to be the basis for the digital section of URTI. Another project of ours is Amalthea. This is a code name for a software-defined radio platform that in its current incarnation is an add-on board for Cynthion. So this is an example of connecting a digital radio to the FPGA on Cynthion and then just using Cynthion as the USB transport. And we have a concept called Hybrid-SDR, which is the ability to create gateware for the FPGA to do digital signal processing for your software-defined radio rapidly and in a hybrid mode with software that's running on your host computer. So your entire flow graph may include some digital signal processing that's done on the FPGA and some digital signal processing that's done on your host computer. And it should be possible to actually configure those functions on the fly and generate a bit stream quite rapidly to configure that FPGA. So that's something we're experimenting with today on Amalthea. Amalthea is a very simple, low-cost digital radio front end that we're developing in parallel with URTI. And what's really great about it is that it gives us a development platform that allows us to build things and test things like our DSP library in Amaranth HDL that runs on the FPGA that would run on either Amalthea or URTI. Now the architecture, how we envision all of these different concepts coming together, is an architecture that may look kind of familiar to you if you're familiar with PortaPack for HackRF. We think that basic architecture of having a user interface board that is separate from a main board, we think that is the right architecture for URTI, in part because it allows the main board on its own to act as an even lower cost USB peripheral. One significant difference between the architecture of PortaPack on HackRF One and the architecture of URTI is that we envision having an application processor on the user interface board, whereas PortaPack H1 uses for its application processor the microcontroller that is on HackRF One. So it is using the main board's processor rather than having its own processor. By having a more capable application processor, we should be able to create more sophisticated software, and also having the FPGA on the main board allows that software to do digital signal processing quite efficiently to enable handheld software and handheld test instrument functions. The battery and display and so forth will be a part of the user interface add-on, but the main board on its own is basically just a software-defined radio transceiver USB peripheral. The USB and FPGA sections of the main board, as I mentioned previously, will be derived from Cynthion. The radio section will be derived in some ways from the HackRF One radio architecture. It will be modified significantly, but it will have a similar architecture to the HackRF One radio section. The main difference being that it will be full duplex and that it will have a directional coupler enabling the VNA function. So what will this look like when it's all put together? My initial concept for a form factor looked like this, and with apologies to Nintendo, you may recognize this as a marketing image for a Nintendo Switch that I've just drawn an antenna onto. This was concept number one, but we fairly quickly advanced from this to concept number two. This was drawn by Martin, who's a member of our team. And this is just a concept drawing, but if you believe that radios should have knobs, I have good news for you. We definitely plan to include one or hopefully two knobs on the device. And we're experimenting with other concepts for user interface, including perhaps a full numeric keypad. One thing not represented in this image is a set of soft keys along an edge of the screen, perhaps. But basically, what we're trying to do, what we envision, is that we would take tactile controls from traditional RF test equipment and integrate them into a landscape mode form factor similar to a handheld game console. And we are, in fact, using a handheld game console as a development platform. I have this console with me, and I have a HackRF strap to it here. And we're using this as a development platform to experiment with user interface concepts and allow us to start working on software for the eventual complete URTI platform. In this demonstration that was prepared by Diego, who's another member of our team, you can see a waterfall application. It might be nice if we actually had a radio signal of interest to show here, but you can see the waterfall working, and it's getting its data from the HackRF in real time. And in this version of the demo, the FFT for the waterfall is actually being computed in the GPU on the game platform, which I think is pretty cool. But Diego also has other versions of this demo, including one with Amalthea that does the FFTs on the FPGA that's built into Cynthion. Another demo prepared by Diego, and this is built on top of some previous work of Mike Walters, who's another member of our team. You may know Mike from his InSpectrum software, which is a popular tool for signals analysis with software-defined radio. This is a demonstration of our Hybrid-SDR concept using GNU radio. And so we have a flow graph here, and various blocks in this GNU radio flow graph, most of them are running on the host computer, but you might notice that serial FFT block, the second block from the left in the flow, is actually a block that is running on the FPGA. And we have this hybrid SDR concept working where you can press play on the demo, and it will, in this case, this is a repeat of a previously built flow graph. So it's actually using a cached bit stream for the FPGA. So it just takes a few seconds to load that bit stream onto the Cynthion, and then the FPGA starts streaming samples over USB into GNU radio. But if we did not have this built already, when you click play, it would automatically synthesize a new bit stream for the FPGA. And that can take a couple minutes. But realize that that is creating a bit stream for the FPGA that includes both the digital signal processing and also an entire USB device core. And the fact that we're able to synthesize that bit stream, including a USB device core, in just a couple minutes, I think is phenomenal. If you are familiar with traditional FPGA development tools, I think you might be quite surprised by being able to do that in 2 minutes. And it's all thanks to the open source tool chain. And in particular, we're using Amaranth HDL, which is a Python-based hardware description language. That is the technology that our Luna gateware is built on, and that we use for the USB device core and for our digital signal processing library. You may be wondering how a low-cost, portable, small, lightweight platform can possibly do the job of all of the test equipment on your bench. And of course, the answer to that is that we will have to cut some corners. We will not have the performance and every capability of traditional test equipment, but we think that we can prioritize needs based on what we envision as being the needs for most radio experimenters most of the time. It may not meet all your needs all the time, but it should meet most of your needs most of the time. If you're new to radio experimentation, we hope that URTI could be your primary test instrument. And if you already have radio test equipment, URTI could be a way for you to take those capabilities with you into the field as a portable test instrument. As an example of kind of the prioritization that we might make, this is an SMIQ signal generator. It's a vector signal generator that I have on my bench. And I took a photo of it because I noticed something about the way I use it. This is an older device, but it's very useful, and it has very sophisticated capabilities to produce modulations. You can give it a vector modulation in either analog or digital input. And but even though it has these very sophisticated modulation options, I want to show you my favorite modulation option, which is off. Almost 99% of the time, I would say, I use modulation mode off when I turn on this test instrument. I just configure it with a frequency and a power level, and it produces an unmodulated carrier. And sometimes I have it sweep through a range of frequencies, and that's mostly what I do with this device. It has these sophisticated modulation options, but when I really want to transmit a custom modulation, I usually turn to my HackRF because I find that its software is more convenient. So this is an example of how you may have capabilities on your bench that aren't really a high priority. But maybe it's not the best example for URTI because vector signal generation will actually be a strength of URTI since it is based on an SDR architecture, right? Perhaps a better example is my VNA. This is a screenshot from an old vector network analyzer that I have on my bench. It's an old one, but it's a good one, and it has great capabilities. And here's a screenshot from a measurement that I made a few months back, actually kind of as part of this project. And this screenshot, what I want to point out is this kind of narrow band across the middle is really the only part of the output that I was interested when I made this measurement. This is a 20 dB swath, and I was interested in the whole bandwidth, the wide frequency range across the horizontal scale, but I really didn't need very much of the dynamic range on the vertical scale, the power scale. I really only cared about things, characteristics that were between 0 dB and negative 20 dB. So my and this is maybe a much more appropriate example for URTI. Compromising on VNA dynamic range is something that we expect to do. We want to make the VNA function useful, but like NanoVNA, it's unlikely to have the performance that you might find in a traditional benchtop VNA. If you have questions about the project, I hope you'll find me outside after the TAPR forum, and or if you just want to chat. But I will try my best here in the last few minutes of this time slot to anticipate questions that you may have and try to answer them now. When can I buy URTI? You may be wondering, and we don't know yet. We ultimately do expect to manufacture and sell it, but right now this is strictly a research project, an open source hardware and software development project, and that is what we're focused on right now, is developing an open source design that anyone can build to have a low-cost, portable, universal test instrument. How much will it cost? We don't know yet. But making the device affordable is a very high priority for us. What will URTI be called? And again, we don't know yet, but URTI is our working title for the project. We do expect to manufacture and sell it eventually under a fancier name, but URTI is our name for it for now. Is URTI the next HackRF, you may be wondering? And no, it is not. URTI will definitely not be called HackRF. We don't know what it will be called, but it won't be called HackRF, and it will not replace HackRF One. It will not be compatible, most likely, with libHackRF, the software library for interfacing with HackRF, and it will not be compatible with hardware designed to be an add-on for HackRF One. Can you please add a favorite feature? Maybe. We are definitely interested to hear about your ideas, any suggestions you may have for the project. I would love to hear about. However, keep in mind that we do have these goals of low cost and portability that are going to limit our ability to add every possible feature. If you're wondering how you can follow the project, here is a URL that is kind of a landing page with links to various development activities and discussions. All of our hardware designs and software for the project are on GitHub or will be on GitHub as they are developed. And discussions for the project primarily take place on the Great Scott Gadgets Discord server, where I hope you'll join us. How can I help? If you are interested in helping with the project, start in the same places. Probably the best thing to do is to join us in Discord and tell us how you would like to get involved. How can I get a beta unit? We do expect to have some beta units available once the hardware design is complete. And when they do become available, we will have opportunities for folks to test, and we will be prioritizing getting those units to project contributors, of course. So if you are interested, come chat with us in our Discord server and maybe get involved in a project now. How long will this project take? We hope to have a handheld beta platform functional within 1 year. And how far along are we now? We've completed the selection of major components for the initial mainboard prototype, and we're starting on the mainboard hardware design. That will be showing up in GitHub very soon. We're already developing a DSP library in Amaranth HDL for the mainboard FPGA, and we're already applying this in, for example, the Amalthea demo that I showed you earlier. And we're already exploring user interface concepts and software that we can build for the handheld platform on a handheld game console that we're using as a development platform. Thank you all for coming. If I didn't answer your question, or if you just want to chat, stick around for the rest of the TAPR forum and then find me outside. I would love to hear from you, and if I have battery left, you might be able to play with the Waterfall Demo that is actually on my handheld development platform. Thank you to ARDC for supporting this project, and to TAPR for your support and for having us here at the TAPR forum.